chapter 9. As you see on the handout, the first handout I gave you with all the assignments, chapter 9 is a very short chapter, yes.
What was that movie called?
Lonely Are the Brave. Lonely Are the Brave. I love it. It is one of my absolute favorites. I actually have it on DVD because I own it down. I can't ever see it all up on TV. I just do. I love it. It's got great actors in it. They're perfect, and the character actors are just every little character, every little actor plays everything perfect. It's just one of those things. Okay, so polar coordinates is what we're starting with today. It's a short chapter. There's only 3 sections. One of them we break up into 2 days, so it'll go pretty quick. Although we have 2 holidays, so it's kind of spread out. And then we'll get into chapter 10. It's a little harder. Polar coordinates, we're going back to radians. Your unit circle will be extremely helpful. Notice our graph is no longer your typical Cartesian graph. It's not your XY coordinates. It changes. Okay. The polar coordinate system has an origin, the pole, an array called the polar axis. So that's the polar coordinate system. Basically what you're dealing with is you're dealing with direction and distance. Polar coordinates are given in r and theta. R being the distance from the pole, and theta being the angle from the x-axis. So angle theta follows the same angles that we use in the unit circle. So the angles are the same angles we use in the unit circle. So we have 2 points to our coordinates. How far away from the center we are and what angle we are going up from on that center. That's how you do polar coordinates. Okay. If you've ever seen a movie where they show a submarine or a naval vessel using radar and the blip on the radar, those are polar coordinates where the boat or whatever the radar installation is the center of the polar coordinate. And the object that's bleeping is distance and angle from where you're at. If you've ever seen those movies, the screens, they look just like that, right? The radar installation is here at the center. The blip that shows up is the distance away from that. That's the R. And the angle off center, off of the axis, that's the angle and direction. Angle and distance, direction and distance. That's how it works. Okay, that's how they work. That's why the screens all look like this, because they're using polar coordinates. Okay. So let's plot a few points here. Remember, the first point is distance. Second point is angle. So if I have 2 pi over 6, that means it's going to be on the second ring out, because the distance is 2, and it's going to be in the angle pi over 6. So my first point, 1, 2 out, pi over 6, that's where A is. Okay. Out 2 units, pi over 6. Part B, 1 negative 4 pi over 3. So we're on the first ring out. Our angle is negative 4 pi over 3. So instead of going the usual positive direction around, you're going in the negative direction. 4 pi over 3. There's pi over 3. There's 2 pi over 3. 3 pi over 3. 4 pi over 3. So it would be right here. That's where B would be. Starting to make sense? C is 5, negative 5 pi over 6. So 5 is 1, 2, 3, 4. It's the outside ring. Negative 5 pi over 6. 1, 2, 3, 4, 5 pi over 6 puts us here. That's where C is. Okay, D. D is a tricky one. And actually, if I have a negative distance, it's a little bit different. Same idea, though. I actually like to start with the angle, particularly if I have a negative one. So I go to 3 pi over 2. So let's see, that would be 1, 2, 3 pi over 2 would be in this direction, would be this one down here, right? That's where 3 pi over 2 is. But what am I going? I'm going negative 5. So here's 0, so negative 5 would actually be in the opposite direction. It would be going up. Instead of going down in the direction of 3 pi over 2, this would be positive 5. I'm going to go to negative 5 up here. That's where D is. So I have a negative direction. I have the same angle. I'm just going in the negative direction. So I'm going positive 5. Ooh, I go negative 5. That means I'm going in the opposite direction of my actual angle. So for E, I have negative 3 pi over 4. First thing I do is negative 3 pi over 4. 1, 2, 3 pi over 4 is here in this direction. But I'm not going in that direction. I'm actually going in the opposite direction. 1, 2, 3. So that's where E is going to be. It's still on the same angle. My angle this way, 3 pi over 4. But this is the positive direction. That's the negative direction in the opposite one. So the last one, negative pi over 3. That would be, here would be negative pi over 3. And how far do I want to go out? I want to go 3.5. So that means I go to the third grade, halfway between the third and fourth ring out. 1, 2, 3.5. Or F would be. Now, here's the thing with polar coordinates. Because we're dealing with angle and direction, think about the unit circle. Every angle on the unit circle has lots of angles that are coterminal with it. You can have positive ones. You can have negative ones. Pi over 4 is the same thing as negative 7 pi over 4. Or positive 9 pi over 4. And so on. There's several angles that line up in that same place that are coterminal with it. So there are lots and lots and lots of angle measurements. And then if we talk about being positive and negative direction, we also have the angles that are completely opposite, but in the negative direction. So for every polar coordinate, there are lots of other polar coordinates that will give us the same point. It's not like the Cartesian plane where you have x and y, and certain x and a certain y always gives us the same way. There's no other way to describe that point other than, let's say, 2, 2. No other numbers will give us the point 2, 2. But in polar form, you have lots of coordinates that will all give us the same point. Lots and lots and lots and lots and lots of points that will give us lots and lots of things that will give us the same point. So, for example, if I look at this next one, I can come up with 4 more coordinates. I can come up with a lot more than 4 if I was really pressed to describe the point 2, negative pi over 3. Now, 1, 2 circles. Negative pi over 3 is about here. So I have this point here that I want to be able to describe, and that's negative pi over 3. And I want to describe that with several other coordinates. I can have that one point I can name with several other coordinates. For example, I can still have 2 units out, and I can come up with different angles that still line up with that one. So I can have the point 2. Let's say instead of going in the negative direction here, I go around in the positive direction to get to there. So that would give me 2, and that would give me, let's see, 6 pi over 3. Subtract 1 would be 5 pi over 3. Same point. Because I go around 5 pi over 3 to get to here. And I can do 2 again. And I can still go in the negative direction and still get another angle that gives me the negative pi over 3. I just go, okay, I'm going to go all the way around and a little bit more to get me negative 7 pi over 3. It's still the same point. It's still the same point. Still the same distance out. I get the same angle for both of them. Now, another trick is, let's say I want to be on the same line here. I want to be on the same line. But I want to think about this instead of being two units out, I want to think about it being -2 units out. I want to think about it, hey, I want to go -2 instead of +2. That means instead of the angle I have here, I want to go with this angle up here. Which if I go positive, that would be, let's see, 1 pi over 3, 2 pi over 3. So I have -2, 2 pi over 3. Gives me the same place because I go around -2 pi over 3, and then I go 2 in the negative direction from the center. And I can still go -2, but instead of going in this direction, I go in this direction, the negative direction on my angles, and I go around 1, 2, 3, 4, -4 pi over 3 in the -2 direction. Circle around to -4 pi over 3, and then go backwards 2 instead of out 2. And we can keep doing this for forever, right? Because we can go around the circle as many times as we want in either direction, and we can keep going and going and going and going and going. There will all be 2 and -2, but these angles, we have an infinite number of choices for the angles to come with it. Okay? So unlike regular coordinate points, which only have one possibility for the way of naming them, with polar coordinates, you have an infinite number of ways of naming them. Generally speaking, we try to keep it between 0 and 2 pi, and then the positive distance makes it work nice, but you can do anything. Okay. Converting polar coordinates to rectangular coordinates. It's actually very easy to go from polar to rectangular. A lot less work. It's very easy. And this is where your unit circle will be very, very handy for you. To find the rectangular coordinate, your x-coordinate is the radius r times the cosine of the angle. That's what the x-coordinate is. R cosine theta. So for this one here, my x-coordinate is 2 cosine pi over 6. And the cosine of pi over 6 is √3/2, right? Yeah, √3/2. √3/2 is √3, so I get √3 for my x-coordinate. Said unit circle, you can get it come in handy an awful lot. The y-coordinate is almost identical. It is r sine theta. So 2 sine pi over 6. The cosine is √3/2. The sine is 1/2. 2 times 1/2 gives me 1. So if you were to do the polar coordinate, take that, lie it on top of the Cartesian plane, those 2 points would line up. Okay. As long as the distance r's line up. Same thing on this one. It's a little more complicated, but it's not that bad. 3 pi over 4. I see pi over 4. I'm thinking √2/2. I just have to know it's positive or negative √2/2 depending upon where I am on the unit circle. I love pi's over 4 because they're always √2/2 plus or minus. You just got to figure out which quadrant it's in. So for the cosine of this one, sorry, the x-coordinate of this one, -8 cosine of 3 pi over 4. 3 pi over 4 is in which quadrant? That would be second quadrant. So the cosine's negative. So it's negative √2/2 times -8 gives me 4√2. And so the y would be -8 sine of 3 pi over 4. Once again, it's in the second quadrant. Sine is positive in quadrant 2. So it's -8 times positive root 2 over 2. So that would be -4 root 2. Really not hard at all. That's an easy one to do. Any questions about that? Okay. Going the other direction is significantly more difficult. Still not hard, but it is significantly more difficult. Okay. Your R value is found using the Pythagorean theorem. X squared plus y squared equals R squared. That's where it comes from. We're drawing the right triangle. Because here's what we're doing. Technically, here's what we're doing. We have our XY coordinates. Here's our point, XY. And it doesn't matter what quadrant we're in. That's X. Sorry, that's X. This is Y. This is our distance R. There's our angle theta down there. And what we're doing is we're going back and forth between them. For the polar coordinates, we have R and theta. We use the right triangle trig to find the X and Y. If we have X and Y, we're essentially doing the same thing, Pythagorean theorem to find R, and we're using trig to find theta. And that's what we're trying to do. That's exactly what this is all about. You have some XY coordinate, and it's going to give you those things. Doesn't matter what quadrant it is, it's the same thing, just your triangles in different places. Okay. So, let's do the first one. I want to find R. That's the easier thing to figure out. X squared plus y squared equals R squared. 2 root 3 squared plus -2 squared is equal to R squared. Plus 4, 16. R squared 16. R is 4. That's the easy one. Theta is the hard part. Theta equals the inverse tangent of -2 over 2 root 3. No, but it's okay with what you have here, kind of from what we're doing, and I'll explain how to figure this one out. So we have theta equals the inverse tangent of 1 over root 3, and I should say -1 over root 3. And this is okay because what is the tangent? The tangent's the y over the x, right? So if we're going back to our unit circle, we don't have this, but we do have stuff that has root 3 in it, right? We have, technically, you can stop and think about this, as the inverse tangent of -1/2 over root 3 over 2. And the -1/2 and the root 3 over 2 are points on our unit circle that work for a particular value of theta for x and y, for the sine and the cosine. Remember, tangent, sine over cosine. Sine of an angle, cosine of an angle, that helps us kind of visualize where we're at. When you end up doing this, theta ends up being 11 pi over 6. Now, the question is, we have to stop and think a little bit. Does this make sense? Because there are other angles that we take theta of, or take the tangent of, that will give us the same thing. In fact, there are two there are two of them in particular that will do this. What quadrant is our original point in? Where's the x and where's the y? Where's our original point at? It's over here somewhere, right? Because x is positive, y is negative, that's where it is, right? So our angle theta needs to come out somewhere over here. Or if you're working negative, it needs to come out some negative value to get it down there. When you're doing your inverse tangent, you need to keep in mind, where was my original point? Is that angle going to work for this? Is 11 pi over 6 going to give me what I want here? Yeah, 11 pi over 6, we'll put that in the right place, because that's almost 2 pi, right? It's not quite, but almost 2 pi. So that makes sense for it to be in that quadrant. But if you took the inverse tangent on your calculator, is it going to give you that value? It's not going to give you this. Your calculator, if you did that, would give you negative pi over 6. Would negative pi over 6 work? Yeah. Because if I go this way, 11 pi over 6, that's the same thing as going this way, negative pi over 6. So it is possible to have that. So if you're using your calculator or something, or using your unit circle, either way you can get the right answer. And once again, there's more than one polar coordinate that will give us the same place where we can use 2 points for. You just got to be careful and keep in mind, where is my original one? Does my angle make sense for that spot?
How did you get the -1/2?
1 over root 3. What I did is I said, well, we don't have 1 as a sign value. We don't have, well, we have -1 as a sign value, but we don't have root 3 by itself as a sine or cosine. But we have root 3 over 2. And if it's root 3 over 2 is one of them, 1/2 is the other one. So what I did is I just put them that way to make it easier to think, okay, tangent sine over cosine, where on the unit circle do we have the sine of -1/2 and the cosine of root 3 over 2? Makes it easier to spot. Does that make sense? That's all that is. Okay, let's do the same thing on the next one. Negative root 3 over 3. Okay, sorry, negative root 3 and root 3. So negative root 3 squared plus 3 squared is equal to r squared. What is negative root 3 squared? Ah, 3. What is 3 squared? What's 3 plus 9? 12, which means that r squared is 12, so the square root is r is 2 root 3. Simplifying your radicals. I love 2 root 3. So my r is 2 root 3. Now I got to figure out my theta, and it's a little more difficult. Same idea though. So I set up theta is equal to the inverse tangent of y over x, right? 3 over negative root 3. Which is actually a version of root 3 over 1. So that would be root 3 over 2 over 1/2. Okay. You kind of got to learn some of these inverse tangents from there. So I end up working it out, and I get tangent equals, or sorry, theta equals 2 pi over 3. Is that going to stick me in the right quadrant? Where's my original point at? It's negative x, positive y, so my original point is up here somewhere, right? Is 2 pi over 3 going to stick me there? If I go around to the angle here, 2 pi over 3, is that going to work? Yeah, that'll work. There's my coordinate. Questions? Okay, we are going to be, yes.
How do you know what the original point is?
XY coordinate. This is an XY coordinate, right? Negative x, positive y. I did not plot it exactly where it is. I said, okay, what quadrant's it in? Is the angle theta going to give us, if we do this, are we getting the angle, is the angle we're going to get here going to work for being in that quadrant? Yeah. And that's just kind of a double check and make sure I'm okay. We've gotten a negative angle. Would that work with a negative x? You got to be careful about that kind of stuff. If it doesn't, then you're going to have to make the adjustments to this, because the inverse tangent's only going to give you, remember, your inverse tangent is only going to give it to you in a couple of places. This is where using the unit circle actually comes in better than using your calculator. Because you know you have a negative x and a positive y, you're going to be stuck in here. So what angle is going to give you this for its tangent? That's kind of why I did it here to the negative 1/2 and the positive root 3 over 2. What angle has this for its y and that for its x, or this for the sine, this for the cosine, on the unit circle to give me that tangent? That happens to be in the correct quadrant. That's what I'm looking for. If I did this one to do the same thing here, this one would actually give me, this inside here would be root 3 over 2 here, and negative 1/2 on the bottom. No, the other way around. Negative. No, it's root 3 on the bottom and 1 on the top. Yeah. I think that's what it is. It's the same idea. You're trying to figure out where it goes and where it lines up. Unit circle comes in real handy on this stuff. Okay, any other questions? Okay. Last but not least, we are going to be doing some graphs. Today we have the absolute simplest possible polar graphs there are. That will change. Okay. Your calculators will do polar graphs. I am not exactly positive how to do them on them because I have not done them on calculators in God knows how long. When you do your chapter test, you will not be using your graphing calculators because I need to know that you know how to do your polar graphs without them, but they're really cool looking if you can make them do it. Okay, they really do look cool. It looks so much cooler than anything I could ever do by hand. They're really gnarly, not necessarily the ones today, but the ones we're coming up against are going to look really cool. Yes, question?
I'm sure I didn't work on my calculator. You did for the
Yeah. So you'll be able to do polar coordinates on this. And I'll look to try to figure out how to do the polar coordinates on graphs. Next time we come, I'll have that set up for both of them. I'm not sure. You have to change the coordinate system to polar instead of your typical coordinates. And when we do conics, we'll have to do the same thing for conics. Okay. So polar graphs, there are two basic ones. These are the most basic ones they are. They have one where r equals a is my equation in polar coordinate form. R is equal to a constant. The radius is set, but the angle can be anything in any direction. If the angle is not given as part of it, the angle is anything. If you have r equals some value, this is a very, very, very simple graph to do. Polar coordinates. For example, the equation, the polar equation, r equals 3, is a circle with a radius of 3. So if you have the equation r equals some number, that is strictly a circle centered upon the origin with a radius of that value. Easy peasy. I mean, you really can't get easier than that. Well, almost than that. The only graph, yes.
Does it matter where you have the radius?
No, they just have to have the radius, whatever they tell you it is. Theta equals some value b. In other words, no radius is given. The angle is set, but the distance from the pole is anything. The angle is set, but the distance is anything. Okay. First one, radius is set, but the angles vary. We get a circle. Second one, if the angle is set, In this case, 5 pi over 6, which is all the way around over here. This is anything going on that angle in the positive direction. That's it going in the negative direction. Yeah, so if you have theta equals some angle, it is a straight line off of that angle in either direction. D2, simplest polar graphs you can come up with. A circle and a line. One has no angle, one has no distance. You just got to memorize which one's which and stuff like that. Once again, when we meet next time, next week, you'll have much, much, much prettier. Bring some for me.
Yeah. You want out?
Which one's what?
Whatever.
What are they?
Actually, it's a George.
What's that? What's on them?
It says cold.
Cold.
Yeah.
It's got cold on it. I don't want to eat something with cold on it. That just sounds like viral to me. I mean, really. It just says cold.
Yes.
It doesn't say what's on there. It doesn't have like, it's got turkey and pepper jack and mayonnaise and lettuce, pickles and onions.
So it's gourmet. I'll take
That's for me. I like it because I don't like gourmet things on something. I don't like avocado. Avocado would be considered a gourmet thing, would it not? Oh, screw that out. I don't. I really just don't care for avocados. I don't like the taste of it. I like the texture. It's just me. I know. My wife listens to. Okay.